Do you hear me? I'm Roberta Baggio, so you will listen to my talks many times these days because I'm working on different projects at the University of Corsica. So today I'm working, as Jean-Baptiste just said, about the project. Okay. So perfect. Okay, it's better now. So the project we have done for the INR FireRes, which it was an INR, sorry, Horizon 2020 project FireRes, which was an European project aimed to improve resilience against extreme wildfire events. So a very actual topic. And so what work consisted in taking a tool we have at the University of Corsica for coupled wildfire atmosphere simulation and develop like a prototypical operational chain which can be useful for decision making. So now I will present briefly the paths we follow to develop this. And then after, Jean-Baptiste will actually show you how this code looks today. So a little bit of introduction. Actually, this concept is more a repetition because we have seen this many times today. But here I just want to point it out that it's more like there is more and more knowledge on why it is important to include wildfire atmosphere introduction when modeling wildfire spread, especially for extreme wildfire events. Because, of course, we have an actual effect of the developing wildfire on the local meteorology. So we don't just have the importance of surface wind naturally, but we also need to implement a double feedback between the developing fluxes of the wildfire and the local atmosphere. So this is the only way we can see phenomenon like pyroconvection, which has the more extreme manifestations are the formation of these pyroconvective clouds like pyrocumulonimbus, but also we have fire-induced winds, and also to observe smoke dispersion on many scales, we need to have upper wind in the atmosphere. So and just to remind why this is important, here it is a picture of an extreme wildfire event that was in 2017 in Portugal, which was characterized by a lot of pyroconvective activity and sudden shift in propagation speeds, which unfortunately result in many deaths about civilians and firefighters. In the next slide, I'm showing, just to recall that we have many types of wildfire modeling. We have seen different modeling approach today. So we have the very small scale detailed models that are used to model wildfire urban interfaces. But here I'm talking about big wildfires. So we are at the scale of 10 and 100 of hectares. So what is used in this context operationally are wildfire spread propagation which are very fast. Like they took just some seconds to run, and so they can provide the forecast prediction of wildfire spread very fastly. For an example, we have for fire at the University of Corsica, developed by Jean-Baptiste. That is also an event-based code, I'd like to point it out. But there are also other very famous approach of this type. So with this type of model alone, we cannot see wildfire atmosphere interaction. So we have to couple this type of approach with the atmospheric codes. So that are like numerical weather prediction codes, like the one that's used for weather forecast, but at a smaller scale. And at the University of Corsica, we have the couple between for fire and mesoNH. Alberto also told about it before. The problem of this is that they are computationally intensive, so they are very slow. And so what we worked on, it was to make it more compatible with the operational needs, so to fast enough computational time, but also to make more efficient all the setup phase. So a little bit of context again. There is not the first presentation today talking about mesoNH and for fire, but a little bit of repetition. We have a double feedback. That means that the wildfire spread code is exchanged with the atmospheric code vapor and heat fluxes. And then the atmospheric code is giving back like surface winds to the spread fire. So in this way, we can model at the same time very high resolution wildfire spread and large scale dispersion of the wildfire plume. And yes, I put like the links to some of the work we made to study the formation of pyroconvective clouds, but also large scale dispersion of a pollutant cloud that was not a wildfire, it was an industrial hazard, but we used like this coupling mechanism to simulate this. What we were working to achieve and what we have of some sort now, it was a schematic workflow of this type. So like we trigger a simulation for instance, given a HTTP request with coordinates of ignition and date. And then the workflow automatically gathers all the data that are needed by the wildfire spread model and the atmospheric code. So this means weather forecast of the day, but also orography and fuel map for the wildfire propagator code. Then the simulation starts, and with some time scale, we have outputs, like hourly outputs, illustrating the development of the wildfire spread. And then at the end of the simulation, a summary report. Okay, so of course we needed to work a lot to automatize all this workflow, but the main constraint was, of course, computational time. So in the atmospheric modeling, it is common to use many nested domains. We have seen it even before, and this is because we need to downscale weather forecast up to a higher resolution domain that is in the one in the middle. That is the one which is actually coupled with the wildfire propagator code. So in our case studies that we showed, for instance, the pyroconvective cloud in Portugal, but also the works that Alberto showed this morning, we used this free nested configuration where the innermost domain was at 80 meters resolution. And here I pointed out that this is the resolution of the atmospheric code, but the wildfire propagator is working at bigger resolution, like 10 meters. And so then we have some sort of coarse graining when exchanging fluxes between the two. And this is because we need fuels that are very resoluted, like 10 meters or so. And this configuration worked quite well for our case of study, but it is not fast enough. It's faster than real time, but not so much faster, that 1x6 2 time at the best. So we looked about a configuration which was more suitable for like emergency response. And at the end, we chose this one, where the nested domains are just 2 and not 3, and the innermost domain has a resolution of 160 meters. So, of course, we lose some detail, but we tested this on some Portuguese wildfire. We had all the wildfire propagation map for these cases. And we also were able to observe pyroconvection, so we were quite happy with the results, and especially because we were faster, like 10 times or more faster than real time. So then in the context of the INR project FIRES, we exchanged with many living labs in Europe, and we asked them to provide us with some spreading, like some wildfire burning area maps or details. They had some about real case wildfire that were familiar to them because we needed to exchange with these living labs, like showing them our type of simulations. And so these are the 3 cases, 3 of the cases we realized. So we have one of the 2022 wildfire in Aquitaine. We are showing here the the developing plume in the smaller innermost domain, but also more in the large scale. And we tested it also in Spain and another case in Portugal. So, okay, a big problem of this type of simulation is that they provide a huge amount of data, because we are talking of a grid with a lot of points and with a lot of atmospheric variables. So every time we have to publish results, but also to show, to provide fast outputs, we need to select the most important visualization. And this is why we changed with some of the living labs, for them to tell us what was more important for them to visualize. And we identified 3 key needs for that. So to identify fronts that are more susceptible to sudden changes of behavior, to map the smoke, to identify regions of reduced visibility, and also to provide a visual plume structure, yes. Okay, so here I'm just showing one for the wildfire of before. Yes, it's just 1 hour time, one picture for 1 hour. But here, for instance, we are plotting the wind at the surface wind together with the region of highest turbulence, the fire front with the faster points, and the stronger upper winds. So here instead I'm showing plots with smoke concentration at the ground evolving in time, together with arrows that are showing the surface speed. And we also have the bigger scale, the larger scale domain, in which we can plot the upper and the bottom surface of the smoke plume. And altitude, yes, altitude of the plume. And so now
That's me.
Yes, now it's you already.
No, yeah, just to so we had that, and then we eventually with Ronan we had the Silex campaign, and so we made several activations of that. So that is so we ended up. So you can go to this address; it should work, and it's about 560 activations. But we had to set up another one, which is because all of these simulations from Roberta takes 1 hour to make 12 hours. So it was a requirement to do that even faster. So we had to do it in 15 minutes. So we went down to 800-meter resolution, and which is a good thing, because the 800-meter resolution you can actually. I don't know if it's. You can actually run it on your laptop. So, if I do that, I don't know if there is a demo effect, but localhost 8080, that is live. So that is running now. So we use this interface to design the one. So we show the wind, and we show like that. So in these things you can interact. So that's a couple simulation running on here. So we can make. So if you want to run your own, please get for fire. So we did that. That's the smoke at ground and the turbulent energy. So we can see the fire merging at some point because and some of the convolution. So you can set some other fire somewhere, or we can activate spotting afterwards. So I will kill that, or we will kill my CPU. So we did that, and so each firecast then is playing or not? Not playing. So every time you go and for each of the fires that is launched automatically by FCI or with you, you end up with a running page like that, and then you have an interactive map where you can look at the actually running simulation, and it's similar somehow very much like WRF-X, or I don't know. It will be, by the way, extremely good to have a standard representation of whatever the firefighter anywhere in the world would like to see, and what color we use for Tiki, what color we use for burn probability, what little picture we have for anything, and to derive that will make it much easier even for the training and everything. But so we have to design our own color things, and that's what the design is Roberta design. So, even for the colors and for all the maps, and eventually, so what else you have is that is a typical report that you also have on the page. So every simulation you end up with a file like that, because they like PDF files. They don't want to look on their mobiles. They want something that they can print. So outside the truck, they'll just put it outside the truck. So they just have a look at it. So it. What?
No,
and so that's the truck. And why is it so slow? Some of the example of the activation this summer, it's a Marseille wildfire, where it was just for us to test, but some of actually the marine pompiers had a look at it because they knew, because of the experiment, if you burn and Fire-S. So one of the important things there was to get where, if the viewport of Marseille is going to get full of smoke or not full of smoke, because many people there, so you don't want full of smoke with the people. And so when you have the forecast like that, one of the outputs is these things. So it's a file. They like a lot Google Earth files because they can open them in whatever GIS they have. And then this is the bottom of the smoke plume. So if it's anything, that means if the bottom of the smoke plume is not 0, that means that the bottom of the plume is over the floor. And so you have also the top of the small plume. And so this is the fact that they need this criteria, which is that help us to minimize the amount of data. And this is a burn area among time, and also the actual burning area. You also have fire power, and for the fire, and they had to learn as well how to read these files and what to do with them. So next, that's the second biggest fire, Reboot, from the MTG. That's a comparison with the MTG imager, not FCI, but just so we remade the simulation like that. And as Alberto showed this morning, in the simulation, no spotting. The fire is kind of stuck in the first village it passes, while in the reality it totally overshoots, and something is happening more about something is happening with the atmosphere. You have that in the coupled simulation, because that's at some point definitely you end up having, so that's altitude, so that will be 2,000 meters. So at some point you do have the plume getting higher than that, so you would expect to have some kind of overshooting, and you would expect that if we had spotting activated, and if Alberto had finished his PhD, we could have started. We could have some spotting and that. So we analyzed it with the radar, thanks to. So just a few words about that. And that's the kind of radar data you could get in France with the operational system. So that's for the Reboot wildfire. So you find it in this address if you want to play. But So for the remote wildfire, there are all the 4 phases of overshooting. You had it, so the starting, and then at the end of the day, you had this at the end of the fire. So it's out. This one is dead. So that's the one. So you can see a little bit the start of the fire, which is very early. So that's going to be here. And then, because the one crazy thing about this fire is it has been catched by 5 different radars. So that means that the frequency you're going to have is not 10 minutes, it's about 2 minutes, because you had... and even with some great radar analysis guy, he can make me the velocity in 3D, most probably. So, and but you can see that some very dense areas of signal, which is yeah. So that's in the same. Eventually, what we did, so in the same firecast, we added every stuff that we found during the thing, the radar, whatever they had, and it's. The things that we did with the okay, some other work with the radar that we did with Adrien, and this coupled model was with it's not and this country fire authority, which is I put the logo, but it disappeared. So sorry about that. And that was the Ballarat fire, where so we had the country fire authority. The logo is here, and Nick had this nice time lapse, and so we could and we had the plume from the radar, Melbourne radar, so we could analyze, especially if the simulation could do like that. I mean. At some point, the overshoots, and because it overshoots, it kind of takes some shear that's coming from upper level. So it seems that it moves the plume and it drives the wind at the ground on a different direction. So because it's like a fire-induced wind shift in some way, and yeah, something happening. Well. That's how we validate. We try to compare our model with the reality anyway. So using different cases, and especially the one in Australia. And that's all. So just another thing, we make the virtual reality experience to do fire simulation. So if you want to try, the headset is there. So thanks a lot.